much. Thanks. Good morning, everyone. Yeah, my name is Daniele Silvestro. I'm a professor in computational biology at the University of Freiburg. And the project that I would like to talk to you about comes from a collaboration with the director of science at Kew Gardens, who is also a biologist and an expert in biodiversity, a professor in environmental economics in Gothenburg, and an AI specialist also based in London. And basically here the question that we wanted to tackle with this idea is how do we best protect or restore biodiversity in a rapidly changing world? And specifically, what can computational methods and AI do to help addressing this issue? And the product we came up with is a software that is called Captain for conservation area prioritization through artificial intelligence. This is a piece of software that is essentially coupling what we know from biology and what we know from landscape evolution, is coupling this with artificial intelligence tools. And in particular, we're using reinforcement learning. This is a type of artificial intelligence that is typically used for example, teaching a computer how to play a game or how to drive a car. So basically, the computer plays a game multiple times, and in the process, it learns how to best play the game. Here, the game that we implemented is conserving or restoring nature. So we implemented a simulated system that reflects what we know about nature and how it changes over time, how it may be affected by climate change and by land use changes. And then the system is read and interpreted by an agent that is basically the computer equivalent of a policymaker, and it's interpreted and translated into a conservation action. This game is played multiple times, and in the process, the computer learns how to best protect nature given an available budget. So this is what the system looks like. And we basically have a spatially explicit model where we can simulate millions of individuals across thousands of species, and we can see how this landscape evolves. I'm not sure if the video is playing here. Yeah. How the landscape may evolve and can be affected by anthropogenic pressure, climate change, and other things. During this process of evolution, the agent will try and place conservation or restoration areas. And it will do so by interpreting the environment that it sees. So as we play this game, we have the agent that is applying a monitoring policy, and the monitoring policy defines how much information can be extracted from this environment. Because this is, of course, a simulated environment, so in principle, we could know everything about it, but it should reflect what a natural environment would look like. So the agent only has access to some of the data, some biodiversity data, for example, or anthropogenic pressure data. We train a model using this simulation framework, and we can see that our AI-optimized policies clearly outperform naive policies in protecting, with the same budget, significantly more species than naive policies, for example, designed to protect the most biodiverse areas. So within the same budget, an AI-trained policy can do a much better job at establishing protected areas in an environment. Our software also outperforms state-of-the-art, but not AI-based programs for conservation planning. This is an example comparing Marksan with our approach. And after a policy is trained using simulated data, we can apply it actually to real data. So this is an example where we looked at 1,500 species of endemic trees to Madagascar. Madagascar is one of the most biodiverse places and one with the highest threats also to biodiversity. So here we identified 22,000 units that could be protected, and with a given budget, we aim to run our model and aim to protect 10% of the range of every species, the geographic range of every species. Our AI-trained policy was able to, with that budget, protect all of the species and to exceed the targets for most of them, whereas running alternative software with the same budget basically was not able to do so. We can also explore different monitoring policies, so like how often does the agent have to monitor biodiversity to be able to best protect biodiversity. So this is, and we can track the outcomes basically of these different monitoring policies. So if we do one-time monitoring and design our whole policy based on this one-time monitoring, we get this type of outcome. We can track different axes, right? So biodiversity, genetic diversity, how much area we're protecting, how much carbon we are storing. But if we do recurrent monitoring, so if the agent has access to biodiversity data recurrently over time, then the policy becomes much more efficient. And depending on the level of detail that we can extract from the system, this will increase further. We can also train different policies toward different goals. So we can train a policy toward maximizing biodiversity outcomes, or carbon storage, or area, protected area. We can also train policies for restoration purposes. So the program will be able to guide us on where and when to basically establish an area for restoration of nature. And we can do that, again, by trying to maximize the amount of carbon that we gain from restoring these areas, or by maximizing biodiversity that we restore from this program. And this will come at a trade-off, which we think our program can help us quantify and measure. So we can train policies with different goals, and use these trained policies to compare outcomes and to evaluate basically the level of compromise that we need to do to prioritize, for example, carbon versus species richness. So to wrap up, Captain is what we think is a future-proof conservation and restoration planning method. It's based on the latest technologies within AI. It can use multi-dimensional input data, so we can use biodiversity data, we can use population trends. If we have them, we can use carbon uptake projections, economic value of the land, the cost of land, and so on. We can incorporate, if available, again, future scenarios. So if we have projections for future climate or future land use, those can be incorporated in the policy as we train the model. And we can optimize toward different goals. The next steps will be to extend this model further to be able to do multi-objective learning, which is basically optimizing a policy toward multiple goals at the same time, so that we maximize biodiversity and carbon at the same time. This is all for me. Thank you all very much.